We're adding 3 every single time. There's a reason I do that, by the way. You don't have to do that, where you do that entire thing. Hudson, what's the second pattern?
Something like the golden ratio.
Yeah.
No.
It's 1, 1, 2, 5, 8, 13.
Okay, but how do I actually get the pattern?
Add the 3 as 4.
This is anyone.
You add 3 and 5 to get 8, then 5 and 8 to get 13.
Yeah, we add the 2 previous.
Wait, that is the second half of the golden ratio. That is it. It's just the second half of it.
Golden ratio is not a list of numbers.
I thought it was.
No, it's related to this list of numbers. It is not a list of numbers.
What is it?
But
I don't even know. Eli said
3 plus 5 is 8, 5 plus 8 is 13, 13 plus 8 is 21. That's how this one comes to be.
Oh, the Fibonacci sequence. That's what it's called. That's what it's called. I knew it.
Okay.
I knew it.
Elena, what's the third one?
For the next number, you have to times the numbers. So times 0.5 is 1,
What am I multiplying by though?
2.
Every time? Yes.
Yep.
Times by 2. Mason, what's the third one? 5 by 3. Jalen, it's the fifth one.
-1. I had it written down.
Grace, what's the last one?
Square.
Yeah. Squared, specifically the previous. So, today we're getting into chapter 10. Chapter 10 is focusing in on sequences and series. We're dealing a lot with our patterns. Today, more specifically, we are going to look at sequences as functions. Now, we're going to write more to do with these patterns. I'm going to be coming back to this sheet a couple times today. But as we go through, we're going to be moving back and forth from getting some more notes to going back and working with those patterns. First, let's talk about what a sequence is. Every single one of the things that I just showed you, those lists, those were sequences. A sequence, by definition, is a list of numbers with pattern. Or at least, that's the simplified version of the definition, is that list of numbers with pattern. Now, when you are talking about a sequence, one of the things that I want to point out is, did you notice that on every single one of these, they ended with that an ellipse, that ... saying goes on forever? And that's a key thing to know about a sequence. Sequences go on indefinitely. We cannot list out an entire sequence. We'd be here our entire lives trying to do it. But another important thing to know when it comes to sequences is their technical definition. A technical definition of a sequence is that it is, first off, a function. Now, there's more to it, obviously, but I'm going to pause right there and ask, what makes something a function again? It's not necessarily polynomials, not necessarily an equal sign. Well, actually, it will have an equal sign, but that's not what makes it a function. Every input
As a set output.
has exactly one output. So every input has exactly one output. Now, speaking of the input, to go a little bit further, a sequence by its technical definition is a function in which the domain what's a domain? It's typically the x values. It's typically related to the x-axis, but it's not always x's. In fact, with sequences, it's not x's. Domain really deals with the input values. Guys, inputs are typically x's, but they're not always x's. But in this case, that domain of a sequence will consist of the natural numbers Anyone remember what the natural numbers are? You're listing integers. Positive whole numbers. Does that include 0 or no?
No.
No, the natural numbers does not. So it's the counting numbers, 1, 2, 3, etc. They're called natural numbers because they're then what you would say out in the natural world. I have one tree. If you don't have any trees, you don't say a number, you just say you don't have any. So, anyway, it's the numbers 1, 2, 3, etc. going on forever. And the range, the outputs, consists of real numbers. So the outputs can be any number that's real, it's just not going to include the imaginaries. Now notationally, when we've dealt with functions in the past, we dealt with function notation like f of x. Sequences don't do f of x though. They do something similar in idea to f of x. Theirs looks like this. This piece here, that a with that little n, and that is actually meant to be a subscript. I just don't write it as small as maybe I should have. It's called a sub n. A sub n is generally speaking going to be equal to essentially the equation, or what's known as the nth term, the nth number in the list. Now that a sub n equals b idea is supposed to be similar in idea to having something like f of n equal to b. It still holds kind of that features of function notation in the idea that if I tell you f of 2 is equal to 4, I'm telling you what function we're dealing with, the one called f. Sequences almost always use a, but they can use different letters if they're trying to tell you about different sequences all in one problem. They'll call one a sub n, the other one's b sub n, the other one's c sub n, kind of like f of x, h of x, g of x type of idea. In function notation, this right here is telling you an x value, and this is telling you a y value. It's essentially telling you a coordinate point. It's doing the same thing in sequence notation. A sub n is equal to b. A is the name of the function. The n is known as the position. It deals with our domain. It essentially tells you that number or where that number is located in that sequence. What am I missing? Ah, that's the other thing. It's also known as the index. That's what I meant. I knew I was missing something. So the 5th number in the list, n is 5. The 20th number in the list, n is 20. That's what that n is telling you. The b, which is just a placeholder, it's not technically b, b is just a variable meant to hold the place, and it's holding the place of the actual term. That term is going to give you those range values, and it's really just the actual number in the list. Now, as we expand upon talking about sequences, we're going to take a closer look at, well, really all the ones from the beginning, but we're also going to look more closely into a couple of particular lists from that first page to get us some information. So, for example, we're going to start with that first list, which was 5, 8, 11, 14. We're going to take a closer look at it to kind of dive into that sequence notation a little bit, as well as to get some features out of it that we're going to bring back to talking about all 6 of those original sequences. So first off, notationally speaking, when it comes to working with our sequence, one of the things you're going to have to get used to seeing is a sub a number equals another number. For example, on this list, my first number is 5. That means a sub 1 is equal to 5. The first number in the list equals 5. A sub 2 says the second number in the list, which in this case is 8. A sub 3 would then be 11. A sub 4 would be 14. What's a sub 5? 17. What's a sub 6? 20. And I could keep going on forever. Eventually, we don't want to keep going on forever, though, so we get to our a sub n, and again, a sub n will, generally speaking, be equal to one of two things. It'll be equal to the equation, which we're not going to deal with the equations today, but we need to know that. Or the other situation where you'll be given an a sub n is equal to a term in the list with unknown position. For example, with this sequence, I could tell you that there is some a sub n equal to 101. Do I know where in the list it is? No. Could I figure it out? Yes. Am I going to? No. At least not today. And I would say a sub n is equal to 101. Now, this is essentially a sequence kind of function notation-y thing that we've got going on here. Now, similar to sequences, similar to functions, we can do something with sequences. Oftentimes when you're given a function, for example, f of x is equal to x plus 2, what are you going to be asked to do with it? It's not an equation you can't solve. There's 2 common things that you are given when you're given a function. Graph it, or sometimes plug numbers in. Graphing is the key thing that I was trying to get to. When it comes to these, you can graph them. Sometimes you'll need to graph them. When it comes to graphing them, remember, n is that domain piece, and the domain is always those natural numbers. And if it's the natural numbers, do I need negatives? No, not for the horizontal axis, which is the n-axis. So when it comes to making my graph, My n-axis, my horizontal axis, will always just be the positives. My vertical axis could be positive or negative depending upon the numbers in the list. Are my numbers in my list negative? No, so I don't need the negative axis here. The vertical axis is the a sub n axis. Now, along my horizontal axis, it's just natural numbers. That's all that can go in, so I just put my counting numbers. Along my vertical axis, I just want to make sure my numbers fit. I've got numbers going all the way up to 20. 1, 2, 3, 4, 5. I've got 6 lines to fit them on, so maybe I'll count by 4s. For no particular reason. You want to count by something else? Go for it. I just chose this. And I can start plotting some points. A sub 1 equal to 5 is the coordinate point 1, 5. Because n is 1, output's 5. A sub 2 is 8 is the coordinate point 2, 8. 3, 11. 4, 14. 5, 17. 6, 20. Anything particularly mind-blowing yet? Nah, sequences and series are a lot of doing things that you already know how to do, but doing it in a different way. At least the beginning of it is. Now, what do we traditionally do if we see a graph like this and we've got an f of x function? What do we do once I got the points? Draw a line to connect them. Don't do it. This is not an f of x. This is a sequence. Do not connect them. If you are connecting the points, for example, I'll draw up here, don't do it. But if you are connecting the points, then you are saying that in the sequence, this point right here exists. Now, I don't know exactly what that point is, but for sake of argument, let's call it 4.515. In sequence, that means we have the 4.5 position. If I'm giving you a number in a list, is there a number in the 4.5 spot? No. Do not connect them. This is a discrete graph. In other words, a disconnected graph. It's not like a linear function where you connect them because it's continuous. So, we don't connect them. The graph looks something like that. Technically, the graph goes on forever. What do you notice about this graph, by the way? It's forming a straight line. It looks linear. It's because it's what's known as an arithmetic sequence. Arithmetic, spelled the exact same way as arithmetic, but pronounced differently. If you call it arithmetic, I'll probably just chuckle a little bit, but I'm not going to tell you you're wrong. An arithmetic sequence is one that, when graphed, it looks linear. Looks like a straight line, but disconnected. The reason that it looks like a straight line but disconnected is what actually makes it an arithmetic sequence is the fact that the pattern is adding the same number from term to term. that number that it's adding is called either the constant or common difference, and is given by the variable d. Now there's one little caveat I need to add to this before I go back to my warm-up sheet and look at those patterns a little bit closer. And it's that pattern that makes it arithmetic, that adding the same number to every term. Now that's not the only way you're going to see a situation where you end up with a linear by adding the same number every time. The other option is technically subtracting the same number every time. Now, there's a reason the definition does not mention subtracting, even though you could argue that it's the same. It has to do with the fact that the focus is on it adding, but if you're subtracting the same number every single time, couldn't you define that as adding something?
Yeah.
Subtracting is adding a negative. So it's still focused in on what you're adding, but technically if you're subtracting the same number every time, it's also arithmetic. Okay, back to this sheet. Okay, we were just talking about the first one. We called it arithmetic. Now, when we deal with arithmetic sequences, there are key features that we need. We need to know that common difference and one other thing, and we'll get to that here in a second. Common difference is given by the variable d. On this first one, what's the common difference? 3. That is my common difference. But there is one other important thing that you need to know about an arithmetic sequence. And this is the thing that you would need to be able to look at it without listing out the sequence, knowing what it is. If someone were to come to you and say, oh, it's arithmetic and d is 3, then what you know is that it's adding 3 every single time. But if that's all you're told, you could get this. Or you could get this. Or you could get a lot of different things. So the other important thing that you need is the starting point. In other words, a sub 1. In this case, a sub 1 is 5. First term is a sub 1. D is what you're adding every time. Is 2 arithmetic? Are you adding the same number every time? No. Is D arithmetic? Are you adding the same number every time? No. Is 4 arithmetic? No. Is 5 arithmetic? Yes. What's D? -5. What's a sub 1? 7.
If you zoomed in one more time, I can see it. Yeah, that's a 7. I'm not even joking.
Is the 6th one arithmetic?
No.
No. Okay, so we're going to come back to those missing 4. Throughout this chapter, we're going to deal with various different types of sequences, but the majority of the time we're going to focus on 2 different types. One of them's arithmetic. The other one we're about to get to. We're going to take a closer look at one of the lists again. This is the third sequence I gave you on the warm-up. What's a sub 1? 0.5. What's a sub 2?
1.
What's a sub 3? 2. A sub 4? A sub 5? A sub 6? A sub 7? I could keep going, right? How long could I keep going? Infinitely, forever. This type of sequence, a sub n, is also going to be equal to the equation. Or a sub n will be equal to a term in unknown position. That is not an arithmetic thing. That is a sequence thing. Much like the others, we can graph. Do I need a negative horizontal axis? No. Do I need a negative vertical axis? Not for this one. Some of them, yes. What's the name of my horizontal axis? Vertical? A sub n. Numbers I put along the horizontal are the counting numbers. I guess I'm going to fit 1 through 6. Oh well, good enough. If I'm fitting 1 through 6, I have to go up to at least 16. Let's see, 1, 2, 3, 4, 5, 6, 7. Dang it. Guess I'm going to count by 3s. There we go. They'll all fit then. Again, the n value is the horizontal, the actual number in the list is the vertical, the a sub n. So 1.5, 2, 1, 3, 2, 4, 4, 5, 8, and 6, 16. Should I connect them?
No.
You still don't connect them. It's still a sequence.
Answer the question.
What does this one's graph look like? What's called exponential. This one looks exponential. How are you supposed to know what an exponential graph looks like?
Hudson's talking about.
Well, you spent an entire chapter identifying graphs in advanced algebra and an entire chapter in algebra. This is known as a geometric sequence. When it comes to a geometric sequence, when graphed, it looks exponential. Though it will be disconnected and there's a caveat. Unless. And we're going to leave that unless blank for just a little bit of time. And we're going to come back to that. Now, what actually makes something geometric is not the fact that the graph looks exponential. It's a feature of geometric, but that's not what makes it. What makes something geometric is that you're multiplying by the same number. From term to term. That number you're multiplying by is known as the common or constant. Ratio. It's given by the variable r. Now, it's going to look exponential, either like exponential growth or exponential decay, unless R is negative. If R is negative, multiplying by a negative flips something back and forth from positive to negative, and it would look like two exponential graphs moving away from the n-axis, or it would look like two exponential graphs moving towards the n-axis. Now, in that case where it's moving towards, it also isn't going to look like multiply. Because similar to arithmetic, having the fact that the definition says adding, but there's the caveat of subtraction, geometric does mean multiplies by the same thing, but it could also look like dividing. Because to divide by something is to multiply by its reciprocal. Dividing is multiplication in disguise. So if it divides by the same thing every time, it is geometric. It just, by definition, we're still focusing in on the multiply. Okay, back to that front sheet. We just focused in on the third one. Said it was geometric. If it's geometric, it's got a common ratio. What is the common ratio here? The thing we're multiplying by every time? 2. And in order to define a sequence, you not only need to tell me the pattern, you need to tell me where to start. In other words, a sub 1, 0.5. Okay, now we skipped over question 2. Is question 2 geometric? No. Is question 4 geometric? Yes. What's R? Not 3. 1/3. To divide by something is to multiply by its reciprocal. The reciprocal of 3 is 1/3. And by definition, R is what you multiply by. A sub 1, 81. Is 6 geometric? No. So, the last two we have on here are 6 and 2. 6 is neither arithmetic or geometric. Neither is 2, but 2 does have a specific name, and it's known as the Fibonacci sequence. Fibonacci sequence is one that you may have heard of before if you've dealt with the golden ratio, because the Fibonacci sequence shows the golden ratio. Also, if you've ever watched the movie Da Vinci's Code, it comes up there.
I haven't seen that one.
That's not where you know it from? Okay.
Probably.
Okay,
I don't know.
so. We're almost done. Okay, today, what you're going to be asked on your homework is identify if it's arithmetic or geometric. Think you could do that?
Yeah.
Identify the common difference or constant ratio. Find the next couple of terms. All doable things. It also says graph. We're going to skip the graphing. A lot of the homework, a lot of the problems are yes or no questions. So, we are on page 663. It is numbers 2 through 50, but the evens. Not all of them, the evens.